Okay, so if we do the math here, what happens? You guys have already done all the math. You end up, you subtract 6 from both sides, right? Divide by -2.
Oh, that makes it
Right.
a negative. So you can't do that one thing to a negative number, can you?
Right.
You can't do it.
Okay, so now if I square root both sides to unlock the squared, then we have some problems, don't we? If I square root both sides, I'm gonna get -2x minus 4 equals plus or minus the square root of negative
Oh, walk.
72. And so, last unit, we would have said n. And it's true. There are no real solutions, okay? But there are some other kinds of solutions. Notice Aspen was very observant here. She noticed that there is no easy out on this one. I told you to give me solutions. I didn't say there might not be any solutions. And there are. They're just different kinds of solutions. So what do we do?
Numbers.
Yeah, we're stuck with this negative under the radical. In order to deal with that, we have to think about, we have to think about what the square root of a negative number might, what might that look like? We could do a couple things. We have some properties of radicals. Let's have all the, Chromebooks should be all closed up, all, phones away, earbuds away, all that stuff, please. So we know that if I have, for example, the square root of a times b. Now, we haven't talked about properties of radicals in detail yet. We're going to get into radicals, functions, and more in the future. But there's some stuff we do know. What could I do with something like the square root of a times b? Let's take an example. What if I had the square root of 36, which I could write as the square root of 4 times 9? What is the square root of 36? 6. Okay, but we could break it into the product of the square root of 4 times 9. What else could I, keep going. What can I do with this? What's a property I could use here to get the same answer using 2 radicals instead of 1? Square root of 4 times the square root of 9. If I have the square root of a product of factors, I can split that into the product of separate square roots. Does that make sense? What's the square root of 4?
2.
Square root of 9?
3.
2 times 3 is 6. It works, doesn't it? Right? So in general, we can say that the square root of a times b equals the square root of a times the square root of b. That's always true, right? So if I have something like plus or minus the square root of 72, I could write that as plus or minus the square root of 72 times the square root of -1, right? But what's the square root of -1? The square root of -1 is defined as I. What does I stand for? I stands for the imaginary unit. So this is an imaginary number. That's a horrible name for it because it makes it sound like it's something that's you can just blow off. It's not real. It's weird. What's it good for? It's not an answer I'm interested in. And for much of our lives, we haven't really been interested in that. You have never used these before, and yet they're very real things, even though we call them imaginary. They're not good for counting, which is essentially what you've done up to this point, is count stuff. Imaginary numbers aren't good for that, but they're good for other things. A lot of science and engineering revolves around the use of numbers that have an I in them, the square root of -1. You got to get past the idea that you can't do this. You can. The square root of -1 is something. It's just not a real number. So we're just going to call it I, and we'll deal with it separately than real numbers. Okay? All right, so that's kind of strange that we can do this, but we can. So what does our answer end up looking like then? we end up with negative 2x minus 4 equals plus or minus. What is the square root of 72 simplified into?
Two.
6 radical 2, yes, we're gonna get
Oh
6
my gosh, I did that right.
radical 2 times I. Okay, so we get two answers, and each of them involve the imaginary unit I. Okay, well, let's keep going. What are the next two steps in order to solve for x? Add 4 to both sides. So that's going to give me negative 2x equals 4 plus or minus 6 radical 2 times I. And then finally,
Divided by negative 2.
divide by negative 2. Okay, but what's our rule? When we divide the plus or minus term, do we need to divide by a negative? No, we always divide by the positive absolute value, right? So we'll just divide this one by positive 2. And then our answer ends up looking like x equals negative 2 plus or minus 6 over 2 reduces to 3 radical 2 times I. Two answers, right? I get the plus and the minus. If I wanted to input these into Moodle, I would have to write this as negative 2 plus 3 radical 2I, or, so comma, negative 2 minus 3 radical 2 times
Why
I.
can't you just make a plus minus?
It just won't do it. It just won't recognize that. You gotta do them separately.
So you don't like solve for I, it's just.
No, that's your answer. It has, you can't solve for I. That'd be like saying I'm gonna solve for 1. I is the imaginary equivalent of the number 1. It's a real thing, it's just not for counting. But it does stuff. It does do important stuff. Like, for example, if you wanted to build a circuit, right? Like if you're designing a circuit, if you're gonna build some speakers, right? And you wanna set up a high-pass filter, so you're gonna filter out the low frequencies to send signals to the tweeter, then you'd have to, they're simple circuits. It's just gonna involve all circuits, all analog circuits, not digital circuits, but circuits that you'd see in like a toaster or a stereo or something like that. They involve just 3 types of things, just resistors. Resistors are like the elements, like when you heat up a stove, that's just a resistor. You send current through it, and it resists the current flow, and it gives off heat, right? It gives off heat as it resists the flow of current. A light bulb is just a resistor. That's all it is. It's a filament that like a regular light bulb, you run, like an old incandescent, now they're starting to be old. They all have all LEDs now, but a regular incandescent light bulb, you just have a little filament, you send a current through that. When you send the current through it, it's a resistor, and it glows really brightly. It gets really hot and glows really brightly, and that's the light it gives off. It's just a resistor. And then capacitors. Capacitors just store charge, and then inductors. And I don't want to get into all the details of these right now. This is kind of physics stuff, but that's all it is, just a mixture of these things. But the thing you have to do is you have to know, in order to design a circuit, you have to know what the impedance is for the circuit. How hard is it to push electricity through the circuit, right? And adding all that stuff up, each of these different kinds of elements contributes to the impedance. And it's a pretty complicated thing until you use imaginary numbers. When you use complex numbers, it's really simple. The arithmetic, you'll learn the arithmetic in the next couple days. You learn all the arithmetic you need to find out what the impedance of a circuit is. It's no big deal. But it relies on these weird kinds of, it relies on I, the use of the imaginary unit. If you want to take a system of lenses, let's say you want to build a telephoto zoom lens, where you can zoom in on things far away and then you can focus. That's pretty complicated. There's a whole bunch of lens elements that are moving together in that thing. When you zoom it out, some of them are getting further away, some are getting closer together. Mechanically, it's a pretty complex system. Very difficult to deal with the properties, the optical properties of all of those individual lenses all at once, unless you use stuff like this, complex numbers with imaginary parts, with the eyes in them. then it gets really simple. So it does very useful stuff for us in engineering and science. You just haven't seen it before. But let's really, this first example was, you're gonna do some stuff like this, but you already know how. I mean, what did this really add to the picture of what you were doing? Think back, last week. The stuff you were doing last week, how different is this? One additional step. All we had to do, really, was this. If I have a negative sign under the radical, what do I end up with? An I. Big deal. Otherwise, it's exactly the same problem we did last week, right? It doesn't change things very much at all, right? But we see that there's a need for this. We are going to get these complex numbers that have these imaginary parts in them. So let's talk about that a little bit. What's this all about? So everything you've ever done in your whole life in math has resided inside this one set called real numbers. You've never dealt with anything other than that. And that's fine. Most of the stuff we do in everyday life involves real numbers. Real numbers, we can divide those into categories. What are the two main subsets of real numbers?
Positive,
Yeah, that's not what I'm talking about. I mean, I can see that, but
they're an amount.
rational and
Irrational.
and what?
Irrational.
Irrational. Yeah. So we could break this up into rational numbers and irrational. What does ratio mean? What's a ratio? I mean, what's our simple math word for a ratio?
Fraction.
Fraction. Yeah. So rational numbers are all the real numbers that can be written as what? Fractions. Yeah, it can be written as fractions, right? So any number that can be written exactly as a fraction is rational. Just a quick review. I mean, we're not talking about this now, but this is probably good to periodically just think about this stuff. So if I take a rational number and I write it as a decimal, what happens? What about 3/4? What is that as a decimal? 0.75 exactly, right? That decimal terminates. It's got 2 decimal places and it's done, and it's exact, right? What about 2/3?
No.
What's that? 0.6666, forever, right? Okay, so that one didn't terminate, but it did repeat, right? And there was a pattern that repeated. And it wouldn't even have to be something like just 6s. It might be a sequence of numbers that repeat over and over and over again. Or it might be something like 0.18333 repeating. We fall into a predictable pattern that never stops, right? So if you write a rational number, any number that can be written as a fraction, as a decimal, one of those two things is guaranteed to happen. It's either going to terminate or it's going to repeat. What's an irrational number?
It's not going to do either of those.
It's not going to do either of those. So if a rational number can be written as a fraction, it can't. Exactly. It can't be written as a fraction. Like, for example, the square root of 2. The square root of 2 is irrational. You cannot write that as a fraction. So is pi, right? Sometimes people say pi is 22/7. Is that true? It's just roughly equal to 22/7. It's an approximation, but it's not. Pi cannot be written as a fraction. Irrational numbers as decimals never repeat and they never terminate. They go on forever randomly, like pi does. We've calculated pi out to billions and billions of decimal places, and it's just keeps on going randomly. There's no pattern. Same thing would be true for the square root of 2. Okay? So everything you've talked about, I mean, there's a lot of stuff to talk about there. Real numbers, there are all kinds of subsets. All the algebra we've done has involved real numbers. But what you got to understand now is that that's just a small piece of the big picture. If you want to look at all possible numbers fall into the set called complex numbers. And they're complex because they've got more than one part. Like complex numbers, we just saw in our last example. We ended up getting answers that looked like -3, for example, plus 3 times the square root of 2i, right? Doesn't that look an awful lot like these kinds of numbers up here, right? Notice that those complex numbers have a part that without an I and a part with an I, right? So we say then that a complex number in standard form we say that word standard form a lot, don't we, in math? So this is the standard way to write a complex number, would be A plus B times I. Okay? That's the standard form for a complex number. And we say that this part right here, the A part, which is the part without an I, is what we call the real part. And the part that gets multiplied by I is the imaginary part. Okay? So for a real number, what is the imaginary part equal to? Like if I take the number -5, for example, the number -5 is technically -5 plus 0i. But 0 times anything is 0, right? So what's the real part equal to in that number? What's the number being multiplied by I? 0, right? So it just doesn't have a real part. Real numbers, literally, real numbers are just a set of complex numbers where b is equal to 0. Okay? Complex numbers in general have both a real and an imaginary part. But you could also talk about pure imaginary numbers, which don't even have a real part. Those are going to be numbers where a is equal to 0. Okay? And so we've just looked at a small subset of all the possible numbers that we could talk about. All right, so let's look at some ways that we could think about graphing this or representing these things, because we got to be able to deal with these numbers. We're not going to deal with them a lot this year, but as you go further in math, you'll deal with them more and more, right? So one way to do this is in what we call the complex plane. Okay, this is a real convenient way to do it. The complex plane looks just like the xy plane, exactly, and it works just like the xy plane. Only instead of an x-axis, we have a real axis, and instead of the y-axis, we have an imaginary axis. So what do you suppose if I took the number, let's say, I took the number -3 plus 4i. How do you suppose I would represent that in the complex plane? Where would the point be that corresponds to that number?
-3 +4.
-3 +4. Yeah. We'll just make an ordered pair out of this, where the real part is the x-coordinate, and the imaginary part is the y-coordinate. And so we would just go back 1, 2, 3, and up 4, and there's going to be the location of that point. Okay? Coordinates are just -3, 4. Okay? Let's try another one. How about the point how about the point 2 plus 7i? Where's that one going to be?
+2, +7.
So it's just going to be right there, isn't it? With coordinates 2, 7. How about the number 6? Just 6 to the right, exactly, right? There is no imaginary part, so the coordinates at this point would be 6, 0. Do you see that? So we just go over 3, 4, 5, 6. So there's 6, 0. How about one more? How about the point -5i?
-5 or 0.
0, -5. They just go down 5. Okay, so these are all representations of those numbers. What if we want to know the size of the complex number, right? What do you mean by the size of the complex number? Well, if I have, let's put one more up there. What if I put the number, how about -4 also? Where's that one go?
Down 4.
What? Just plain old -4.
Back to the left 4.
Yeah, it's just gonna be right there, isn't it? So what's the size of that number? What's the size of the number -4? What do we mean by that?
How big is it? It's plus or minus 4.
No. The size of the number -4, what we mean by that is how far is it from 0?
It's
4.
-4.0.
It's 4, right? It's located to the left, but the distance from the origin is 4. What's our function that gives us the size of a number regardless of sign? What do we call that? We've dealt with it a whole bunch already this year. If I input -4, it's going to spit back an answer of 4 because that's the size of the number.
Their lines
Absolute
look like.
Absolute value, sure, yeah. So really, the size of the number is just its absolute value, right? Okay. And we have a math word for size, it's called modulus. So the modulus of z is equal to the absolute value of z if it's on the real line. But what do we do if it's a number that's out here somewhere, right? What did we say the size of a number was? The size of a number, or the modulus, is just the distance from the origin, right? That's easy to do for pure real numbers. It's just going to be the absolute value. You know, how far is it along the real axis from 0 to the number, right? Now, is it a coincidence, just a quick question here, when you guys, all the way going back through first grade, when you talked about numbers, you always talked about numbers on a number line. What is the real axis?
The positive.
It's just the, well, positive and negative. It's just the number line. It's what we call the real line. That's the number line you always talked about. How was that oriented when you talked about it? Was it vertical or horizontal?
Horizontal.
Oh. There it is, right? It's just a piece of the complex plane, right? Okay, so now we gotta go a little further with this. What if we took the number -5i? What's the size of that number? It's going to be 5, right? Because it's a distance of 5 from the origin, right? So when we talk about a modulus or a size of a number, it's always positive. We just want to know the length of the line. And usually we represent these as a vector, but I won't. That's just a fancy name for an arrow. So for example, if we want to talk about this number here, we can represent it as an arrow or a vector starting at the origin and ending at that point. And the length of the arrow or the vector is the modulus. Okay? So in this case, it was simple. In this case, the length of the vector, we can just count. It's 1, 2, 3, 4, 5, 6, right? In this case, it's simple also. It's just the absolute value, or we can count, right? The absolute value of -4 is 4. What is it for this one? Well, it's the same thing, right? Okay, it's just going to be the distance from the origin to that point. But what about this one? That's a little tougher. If I want to find the size of this complex number, is it bigger or smaller than 6? You can't just tell by comparing them, right? We got to think about the length of that line, or that vector. How would I do that? Say it again. I can't just add them together. It's a little more complicated than that. But we could think what these represent. It's like a roadmap for an ant that's going to crawl from the origin up to this point. What are we telling the ant? Why are the numbers 2 and 7 significant? You could say what to the ant? It's a smart ant.
Go up 7.
Yeah, we're going to go, go right 2, horizontally 2, and then go vertically 7, right? And that would get them to where you want them to go. Okay, so let's break those into pieces. Let's just think of this as being a horizontal part and a vertical part. And what kind of triangle did I just make? A right triangle, yeah, right? And so we have one leg is 2 and one leg is 7. Think back to geometry. How do we find the length of the hypotenuse of a right triangle? What is it? Yeah. This is, if you don't remember anything, this is one of the things you gotta remember from geometry. Pythagorean theorem, right? This is just a squared plus b squared equals c squared, right?
That's my stuff.
Right? So 2 squared plus 7 squared equals the length of this line, right? The hypotenuse squared. Let's call that z. Because typically z is what we use to represent a complex number. So we'll just call it z. So then we just have the equation. Excuse me. We just have the equation z squared equals 2 squared plus 7 squared, right? Well, if I want to solve for z and it's being squared, we know what to do. How do I undo squared? Square root. So z equals, we're only going to take the positive answer. I know there should be a plus or minus there, but we said that a modulus is always positive, right? So we'll take the positive square root of 2 squared plus 7 squared. What is that? 4 plus 49? Square root of 53 is the size of that number. We could make that a decimal if we wanted to. That's about 7.19 or something like that. So it is a little bit bigger than this number. It's further away from the origin, right? Does that make sense? How did we get an answer? Well, let's generalize that first. So let's say this time we're not going to pin it down to a specific number. Let's just take any complex number in standard form. So what if we take the number a plus bi? What are the coordinates of that complex number in the complex plane? Over A and up B, right? Okay, so let's start with a fresh complex plane, and let's not be specific. Let's not pick values for A and B. Let's just be totally general. Okay, so we don't know what A and B are, but let's just, for convenience, let's assume that they're both positive, but they don't have to be. Right? They could be negative. So if we have the complex number z equals a plus bi, then there it is, and the coordinates are ab, right? And so the length of that vector is the modulus. That's telling us what, it's like an absolute value. It's like a generalized absolute value. It's absolute value on the real axis, but it has a slightly different meaning when we're off the real axis, right? So if we know then that the lengths of these sides are A and B, then you guys just told me by the Pythagorean theorem that z squared equals a squared plus b squared. If we square root both sides and we keep the positive answer, we just end up with z equals the square root of a squared plus b squared. There's our formula right there, right? That's how we calculate modulus, and to remind us what it is, we'll put absolute value bars around it. So that's our formula for calculating the size of any complex number, the modulus of the complex number, right? So let's go back and let's think about this one that was down here at 0, -5. Well, if we want to calculate the modulus, A is 0 and B is -5, right? So then the modulus is the square root of 0 squared plus -5 squared. What is that? -5 squared is 25. What's the square root of 0 plus 25? 5. Which you already told me. We could see that pretty easily, right? But it works. Okay? try one more here. You guys try this one on your own real quick. What if we have a point out here, let's say over here in quadrant 2 in the complex plane, where we have z equals -3 plus 4i. So we did that one, right? We go back 3 and up 4. So there's the point. Try this real quick in your notes. Calculate the modulus. What are the coordinates? Real part, imaginary part? -3, 4. So A is -3 and B is 4. So try that one. What's our formula for modulus? Square root a squared plus b squared. So what values are we plugging in for a and b? Remember, you gotta put the -3 in parentheses. You gotta put a negative number in parentheses when you square it. And so what's that give us? Square root of, square root of 25, what is that? So the green number and what color is that? Fuchsia? Pink? Pink's good enough, I don't know. But the pink number and the green number have the same size. They're just located in different places in the plane, right? With the same modulus, okay? All right, so one last thing.
Are you colorblind?
What's that?
Are you colorblind?
No. I just don't know what you call it.
I am.
Are you? No. I don't know what you call that one. I haven't found my signature color yet. I don't know that way to get that.
I'm not actually.
You found your signature color, Trent?
Yeah,
Have you?
blue. Dark blue, not light blue.
Oh, okay, there you go. Okay, so let's try this one here. If I is equal to, the definition of I is the square root of -1. Last thing I'm gonna leave you with, this kind of sets us up for some stuff we'll look at the next couple of days. What's I squared?
That is. It's
Yeah, it's -1, the square root of -1 squared. Well, a square root and a squared cancel each other, and so what do you get? -1. I squared is equal to -1. How about that? That's strange. For real numbers, the square of any number is always positive, right? Could be 0, I guess, but it's always non-negative. But for, this is not a real number. It's an imaginary number. And so we get -1. Well, what's I cubed going to be? Isn't I cubed just the same thing as I squared times I?
Yeah.
Right? We could break that down into I squared times I. Well, what's I squared? -1 times I. So what's -1 times I? Just treat the I kind of like an X. I mean, just treat it like a variable. It's just
negative I.
negative I. How about that? So what about I to the 4th? We could make that something like I squared squared, right? Everybody agree? Properties of exponents, I to the 4th, we could write as I squared squared. If I take a power to a power, I multiply the exponents. So we get -1 squared, which is what?
Negative 1. Oh.
Okay, so now let's see if we can see a pattern here. So we get I to the 1 equals I squared equals negative 1, I cubed equals negative I to the 4th equals 1. So what is I to the 5th?
And 1.5.
We could make that any convenient product of powers of I. What if we did I to the 4th times I to the 1? I to the 4th is 1, times I to the 1 is I to the 5th is I.
I don't have any idea.
See what happens? Well then, what did we do? We just looped back to there. If I to the 5th is the same thing as I to the 6th must be the same thing as I squared. Right? See what I'm saying? I mean, we could if we wanted to. If I want to take, this is going to get pretty boring. If I take I to the 6th, I could write that as I to the 5th times I to the 5th is the same thing as I times I is I squared, it's negative 1. We're just going to keep getting the same pattern every 4 powers. I to the 6th is negative 1, what's I to the 7th? What's I to the 8th? Okay, so you tell me, here's my challenge question for the end of the day. What's I to the 39th?
Well, I just have to go.
It's 1. Yeah,
It's either 1, negative 1,
no, it's
negative I, or I.
It's I.
It's I, how'd you get it? Actually, no, it's not, hang
Oh,
on.
no, it's not?
Nope,
Oh, it's negative
Oh,
I.
negative
what is it?
1.
No.
1.
Now think
Okay,
about
because
multiples of 4. 39, if we divide 39 by 4, what do we get?
We don't.
Uh,
You get a point.
10, oh,
You get
It's like
9
9
with the remainder of
1.
2, 4, 3.
3, right? Because 4 times 9 is 36, right?
That's correct.
So it's negative I, because where would that put you? So if
3.
I to the 36, that's an even multiple of 4, right? Anything to the 4th is just 1. So it's like we're starting over right there, right? So whatever the remainder is of this power of I, that's just how far we walk down from the top.
So if it was 40, it would be 1.
It'd be 1. Yeah. Exactly. How about that? Okay?
What?
Too far.
I see what planet I'm on.